this tutorial, we will show you how to create a voltage structure using Voronoi cells and Kangaroo physics engine. We will start with a Voronoi created out of a bunch of points. Then we will convert this into a base mesh, followed by some Kangaroo goals that would create the voltage structure, which looks something like this. You can check out our Patreon page to access the Grasshopper file for this project, as well as other projects on our YouTube channel. We start by creating a Voronoi. Create a rectangle of roughly 110 by 110, and this you can vary. Populate it with 24 points, and let's use a seed value of your choice. Use the Voronoi component. Next, we would like to retain only these edges and would like to remove these edges. In order to do that, we explode these curves. Now, because the output from Voronoi were individual polylined curves, when we explode them, we get duplicated lines for these segments. So these are all duplicated lines. So the first thing that we do is to use remove duplicate lines. Now this component can be found under Kangaroo utilities, remove duplicate lines. So we put this and ensure you flatten this, so you remove all duplicate lines. So we have 73 unique lines. Now out of these 73 unique lines, we want to find which of the lines intersect with the or coincide with the rectangle, the initial rectangle that we created, which is this one. So to do that, we find the curve middle just in here. We just hide all of these, keep this on, and we check the distance using curve closest point. So here's the curve, and here are the points. So we get the distance, and the lines which coincide with the rectangle would have a distance of 0. So we need to find all the distances that are 0. So we can use a simple larger than function which says if it's greater than 0, call it. Once we do this, we get a true and false statement. Just to be on the safer side, let's just use a value which is slightly more than 0. Okay, now we use this to dispatch the curves. So here are the individual lines. Here's the dispatch pattern, and just create a line, hide everything else, you get the line network. So that's step number 1. Copy it over here, make it pink. So this is a color strategy that we follow, where output from one step is highlighted in blue and the input for the next step is highlighted in pink. The next step for us is to create an offset of each of these lines on both sides. So we need to offset these lines on both sides to create a base mesh. Take the lines, use the offset curve, use a distance value in both positive and negative because the offset needs to be done in both directions. And we want this offset to be done for each curve. So we craft this list. The output is the same curve branched into 2, showing a positive offset and a negative offset, and the second curve being branched into positive and negative. So in order to loft these, we need to branch this or get rid of this branch so that these are grouped together. We do this using trim tree. So now we have both the positive offset and the negative offset in the same branch. Use loft, flatten this tree and use something called region union, which could be found under intersect, shape, region union. This component combines all the rectangles that we had into a single polyline based on the intersection, and then using boundary surfaces we can get a single surface output. So that's step number 2. To do this, we copy these lines, get the endpoints, merge the start and end points into a single point parameter, remove duplicate points. Now with this list of 46 unique points and the initial list of 108, we need to find repetitions. To do that, we choose member index. For the set, we use these points, and for the member, we use these points. Here in this output, we get the number of repetitions of each point, and the logic applied over here is that the corner points would have 0 repetitions, because looking at the endpoints of each of these lines, this does not have any further branching, whereas all of these lines gets branched into multiple lines. That means they'll share a common point. So we take this count value, we use a mathematical operator, we use less than 2, get a true and false statement which can be used to dispatch these points. So we have a list of corner points, all in green, and the other list is a list of all central points. For the next step, we need to identify 3 closest points to each of these central points. We do this so that we can create these lines and break this surface into quads like this. For that, we take these central points, we take the surface, let me just copy this. We deconstruct the period. You get the points. You get the curve closest point. So here's the point, here's the... So we need the closest points. So here's the point, which is the central point. We graph this, and then we got the vertices, which is the count, which is the cloud of points, and the number of points, the number of closest points we want are 3, and then we get a list of 3 closest points. Draw up a line using the line component between these two, graph this, and there we have it. Now once we have this line, we would need the initial line as well, which is the initial line network, which can be copied from here. Bring this in, merge it over here, flatten the input, and then use the surface to create surface split. So here's the surface, here's the lines that you want to use for splitting it, and we get a total of 107 surfaces. So at this point, if I hide everything, this is what we get. These are the surfaces. We convert these surfaces into VLEPs. We convert these surfaces into meshes using simple mesh, and further subdivide this using Beaverbird's Catmull-Clark subdivision. Before we subdivide, we need to join this. So we go to Beaverbird, join in weld vertices, set this boolean to true. Now we use the quad split subdivision. Set this to fixed. There we have it. The mesh subdivisions are in order. Just to be sure, let's go to mesh. Let's get the mesh join component. Also the weld vertices to ensure we are building all unwanted vertices. And here's our starting mesh. For the next part, we'll use Kangaroo to anchor these edges of the mesh and apply a length code to the remaining edges such that it smoothens out in this form. In order to do that, we must first find these edges from the mesh. We start by identifying these lines from our surface. So here's the surface. And for reference, we can bring in the points, the corner points. Find the naked edges. Curve closest point. Here are the points. Graph this. Naked edges. We need to find distance that's 0. So we can use this to dispatch. Now, in numerical values, anything above 0 or below 0 is considered as true, and anything that is 0 is considered false. So you can use a numerical value as a true and false statement as well. So we take the distance, we take the edges, and we get all the false, that is these corners. Now once we have these corners, use mesh edges, get the naked edges. Out of these naked edges, we find the curve middle, or a point on curve, and we see which of these points coincide with these lines. So we again take the same point, closest curve component. Here's the point, and here are the curves. Now here we will be flattening this list, and this list would be grafted. We again look for a distance parameter that is 0. We can use the same dispatch, naked lines, distance. Now for some reason the distance is not registering the way we intended, so let me use a mathematical operator and set this value to less than 0.01. Using the curve closest point component, this tends to happen sometimes that a distance that you expect to be 0 is sometimes displayed as a very small value. So if we do this and then use smaller than, there we go. So we get all the corner edges. We join these curves and explode them, and use the vertices as anchor. So that's goal number 1. Second goal would be edge length. So we take this mesh, we use a factor of 0.1. That's the second goal. And for the third goal, we will apply a separate goal for these edges. To do that, we'll take the remaining line segments, which are over here. Flatten this. We'll use duplicate. We'll use remove duplicate lines component to ensure that we don't have any duplication. Use the length line component. So here's the line. For the length component, we will use the length and multiply it with 0.25 or any value which is smaller than 1. That's the target length. In addition to this, we will also use show. And twine all of these together. Use Kangaroo solver. And there we have it. We run the solver. You get the base mesh. That's it for part 1. Part B of this tutorial covers the conversion of base mesh into a Voronoi vaulted structure such as this one. To get access to this video, consider subscribing to our Patreon channel. Link is in the description below, where you will get this entire Grasshopper definition documented into various steps, along with instructions on when to start or toggle various Kangaroo solvers as well as data dams. You will also get access to all the plugins used in this script. So do consider subscribing. Thank you for watching, and I'll see you in the next one.